6.3, we're looking at radian measures now. For everything up to your trigonometry so far, you've been dealing with degrees. In walks, a more important measurement, which is the radians. I explained there in 6.1 why degrees is 360. The radian measure is naturally occurring, and that's why we're going to use it, and that's why it's the default on your calculator. Well, let's look at getting started. A unicycle wheel has a diameter of 70 centimeters, and it rolls 15 meters. Well, wait a minute. First, before we can even start, we need to get everything into the same units. So let's change 15 meters into 1,500 centimeters. Approximately how many revolutions does the wheel make? Well, we can take it and say, how many times does 70 go around and around? Our circumference is 1 revolution. So our circumference is 2 pi r, or pi d, whichever way you want to do it. I'm going to use 2 pi r. I just like that formula better. So the circumference is 2 pi, and the radius is going to be 35, which really comes out to the 7. And I want to know how many times does that wheel turn in 1,500 centimeters. So let's divide them then. So 1,500 centimeters divided by 2 pi times 35, which gives us about 6.8209, so about 7 revolutions. Now we want to know how far does this turn, how many degrees is that, those revolutions. So we've got the 6.8209 times of 360 degrees. So I don't want to use my decimal value, so I'm just going to plug it right back in. I'm going to say it's 1,500 divided by 2 pi 35 times 360 degrees. That will give me how many times it goes around. It goes around 6.8 times of 360. Punch that into our calculator. Gives us 2,455 degrees, 0.5334. So approximately 2,456 degrees. And that's how many times it goes around and around. To construct your understanding here, this is exactly really what we did in 6.2 with your math lab. You brought this information together. So let's look at it. We've got a radius of 4 units, and we're talking BOA on this first one. Well, that angle, well, we know that that's a 90-degree angle there. So that's 90 degrees. Now, the length of an arc has a fraction of pi. We're talking about the arc length, and that was the whole purpose of your 6.2, is to develop this arc length. We know that the arc length is a portion of the full rotation all the way around. Full rotation is circumference. Circumference was 2 pi r. And we want to know what portion is the 90 degrees. So that gives us 90 degrees divided by 360, which is 1/4, of 2 pi r. Let me write it a bit bigger over here. Okay, so this is the arc length of AB, or BA, whichever way you want to write it. So then we've got 90 over 360. That's the portion, the percentage of our rotation around, times your 2 pi radius was 4. Let me plug it in. That gives us 1/4. Oops, 1/4 of 8 pi, which is 2 pi. Okay, now POA, we've got to find out how far is that one. So angle POA, we're going to look at what is that angle. Well, in order to do that, we're going to use either cosine or sine and make a triangle. I know my x value, I know my y value, I know my r value. I could use cosine, sine, or tan, whichever one you want to use. I'm going to use cosine. So cosine of, let's just call it angle P, is equal to the x over the r. The x is 2, the r is 4. So cos of P equals 1/2, and P equals the inverse cos of 1/2. Or noticing, hey, 1/2, that's the unit circle thing. Then angle P is 60 degrees. So let's put it in there, 60 degrees. And follow the same thing. Let's do the arc length of POA. So arc length of PA is equal to, we know that we have 60 degrees out of the 360, and that's the proportion of 2 pi r that we've got going on there. So then we've got 1/6 of 8 pi, which produces 4 pi over 3. That's the length as a fraction of the pi. And I could continue with this for the other two, but the idea is really going to be the same. We find the angle, and then we do a proportion. But we're not going to be talking about many circles with a radius of 4 in this course. We focus on the unit circle with a radius of 1. And that's where we move to now. So we are taking all of this standard position on the unit circle. Much more powerful. So we've got an angle now of 108 degrees. And we want to know what is the length that's subtends. Subtends just means closes off. If you built a fence here and you built a fence there, what would finish off your fence so that your goat doesn't get away? Look at that beautiful goat. I think you need some horns. There we go. I'm going to change it to a dog. It looks more like a dog now. So the proportion that we have now is the arc length divided by the circumference, or 108 over 360. That tells us what proportion of the full 360 circle we've got going on. Arc length is talking about 2 pi r, and I'm going to add that in here. The arc length is the proportion of 2 pi r, but my r is the unit circle. R equals 1. So my proportion is 108 divided by 360 times 2 pi. The radius was 1. So that gives us 3 pi over 5. Which then I see a typo in your book there. That should be 3 pi over 5. Because this right here, 3 pi over 5, is talking about the same thing as 108 degrees. That can be a way of talking about that angle. The arc length is 3 pi over 5. And it's 3 pi over 5 of whatever the radius is. If the radius was 4, it would be 3 pi over 5 radiuses. Well, that brings us to the measure of a radian. The radian is the arc length, what proportion of the circle compared to the full. The full is 2 pi r, or 2 pi radians, all the way around. The definition of a radian is take the radius of a circle. Take that length, like let's say I go and I take a piece of string and I cut it that length of a radius. I take it and I put it along the arc of the outside, and then I cut my piece of pie back in. So I got my pizza there, a radius, long by radius. That is a definition of 1 radian. It is the arc length that is 1 radius long. Whatever angle I have, whatever it be, is going to be how many radians I have on the outside when we compare it to the proportion of the full circumference that we're talking about. And all they're doing is showing here that if we put one circle inside the other, if you double the radius, you're going to double the amount of arc length that you have to travel by. Or in other words, the arc length depends only upon the angle that you're rotating and the radius of the circle. And for our purposes, the radius is almost always going to be a radius of 1 for the unit circle. That means that to go all the way around the unit circle, 360 degrees, whichever direction we go, 360 degrees all the way around, is going to have an arc length of that's the same as the circumference, 2 pi r, the circumference. R is 1, so the arc length of the unit circle is 2 pi radians. And if you want to know what approximately 1 radian is equal to in degrees, take 360 degrees divided by 2 pi, which gives us approximately 57 degrees. 1 degree is pi divided by 180 because 1 degree is 2 pi and 360. 2 pi and 360 degrees are the same. They are identical. So just take that down to lowest terms. 1 degree is going to be pi over 180. And this is your important part now. 1 radian is 180 over pi. 1 degree is pi over 180. All the way around the circle is 2 pi. Halfway around the circle is going to be half of that, just pi. So if 360 degrees is 2 pi and 180 degrees is just pi, what would 60 degrees be? Check it out on your bit.ly link. Let's see what you can do with it. And as you're doing that, just as an aside, radians is not the only other measurement of the angle. We've got degrees that we talked about for all the way up to now. Now we've got radians, which is talking about the proportion of the circumference. Then there's another one, which we're not going to be using in this course, but it's gradians, grad, G-R-A-D. And that's 1/100th of a right angle, which actually makes 400 grads in 360 degrees, or 400 grads in 2 pi radians. All right, let's try this out. Let's go through a process now. You got 170 degrees. You got to be able to convert it into radians. This is a must on your diploma exam. Got to be able to convert back and forth very efficiently. We know that 1 degree is equal to pi over 180 degrees. 180 there. And that will turn 1 degree into radians. So in order to do this, we're saying we have 170 of those degrees. So that means 170 degrees is going to be 170 times of pi over 180. And now just take it down into lowest terms, which is 17 over 18 pi. Just take your 170 over 180 down into a lowest terms fraction. That's the exact value. So when they ask for the exact measure, this is the exact value. Still got a pi involved in it. To take it to your nearest hundredth is now when we plug in the pi symbol on the calculator, and we get approximately 2.97 radians. Because radians is the default, we can just not write the units and make the assumption if we're in exact form. 17 pi over 18 is assumed to be in radian measure. So if we're ever talking in a context that's dealing with an angle, if we're talking degrees, we must put the degree symbol, or else it's assumed to be radians. So the ways that you could write this, you could put radians, or you could just write rads, rad, R-A-D, that's the short form, or you could have left it blank, and I would still know that you're talking about radians. All right, let's go from negative 12 pi over 11. We need to convert that. First of all, we've got to sketch the angle, and we've got to talk about it in degrees. I want to sketch it first, because it's actually easier to sketch radians than it is to sketch degrees. We've got a negative angle, so we're going clockwise. Now we've got a proportion of 12 over 11 of pi. If I was talking 11 elevenths, that would have been 1 pi. And I know that 1 pi is 180 degrees. So 11 elevenths would get me to here. 11 pi over 11. But I have 12 pi over 11. I have to go a touch further. 1 more 11th to be exact. Which puts me there. And I could be able to make my triangle if I'm looking for standard position angles. So in here is my reference angle. If 11 elevenths, or actually negative 11 elevenths, got me to the 180 mark there, and I still have to go to 12 elevenths, inside the triangle would have been 1 pi over 11, or pi over 11 inside the triangle. Let's check it out. Let's change it to degrees so we can see if it's in the right quadrant for us. In order to change the degrees to degrees, we've got negative 12 pi over 11. Pi is equal to 180 degrees. So a nice thing is wherever you see pi, you could slap in 180 degrees. Negative 12 times 180 over 11. Then you punch that into your calculator, and it's approximately, where is it? We'll go negative 196.4 degrees. 196.4 degrees. Negative still, so we're going negative, that's 180. Oh, look at that. We are still going a little bit further. And how much further is the question here? And that triangle inside, which is the same as 1 pi over 11, is, we go 196.4 minus the 180, we get a reference angle inside of 19.4 degrees. Okay, and then the last one, we've got 7.5 radians. I can't just go and find the pi and put 180 in for the pi. Can't use that little trick. So I got to have a little bit more to do. Taking 7.5. 1 radian is 180 divided by pi. We're going to multiply by 180 and we're going to divide by pi. And that will get us into our degrees. That gives us 430.0 degrees approximately. We're going to talk about coterminal angles now. Just like we did with degrees, we're going to start with an angle of 2 pi over 3. But wait, where is that even? I encourage you to stay in radians. Don't convert things Resist the temptation to convert things to degrees and try to do your work in degrees. You will slow yourself way down, and you will not understand what radians are really talking about. If you put a little bit of time into understanding it here, it will really pay off huge. Radians is fraction-based. We've got pi. I know that pi is 180. That's the one thing you really need to remember. Pi is 180. 180 is pi. I am going 2/3 of the way to pi. If I'm traveling along, that gets me half of the way to pi. This is going to be pi over 2. I want to go 2/3 of the way to pi. So I'm going to be here. That's 2 pi over 3. 2/3 of the way to pi. To get back to there, I could go any multiple of 360 degrees, which we've just discovered is 2 pi. So I can go any multiple of 2 pi in a clockwise or a counterclockwise direction. Doesn't matter. I will get back to the original. So we go 2 pi over 3 plus 2 pi. Well, I've just got to change it into a common denominator in order to add. Or we could use a little trick. 2 times 3 is 6 plus 2, 8. That's how we got that numerator. So 2 times 3 plus 2 times 3 plus 2. Whoops, that looks like a multiply again. 2 times 3 plus 2 gives me 8. If I add 4 pi, that's a second time around. Use the same little trick. 4 times 3 is 12 plus 2 is 14 pi over 3. But we could also go in the clockwise direction. That's just subtracting the 2 pi. 2 times 3 is the 6. That's a negative. And then we go 2 minus the 6 gives us negative 4 pi over 3. We're back at the same spot. Do the same thing, go around 4 pi, twice around the circle. We get negative 10 pi over 3. It's just telling us how many thirds we've gone around, in which direction. Which brings us back to that general solution stuff. We've got our answer plus, we used to do it, we did it as 360, slap in the n. I don't like the k so much, I'm going to use the n. We've got 2 pi, because that's the same as 360, n. I'm going to put the n in between, just the way that they're going to put it on the diploma. 2n pi, and we've got to define n is an element of the integers. I or z works. Alrighty, another second question. Which of these angles is not coterminal with pi over 4? Can you get to there in the multiples? Try it out. And I give you now your full unit circle. This is what you're either going to be memorizing or, I highly recommend, understand. Just be able to know your quadrant 1 and apply it to all the rest. I will show you some tricks for getting all the way through next class. To be able to develop this unit circle really quick, really fast. A lot of patterns involved in there. The hardest thing for you is going to be the degrees. All the rest follows a pattern that's very predictable and easy to use. Okay, I want to know the exact value of sine of negative 13 pi over 6. Whoa, they said exact value. That means we're using unit circle every time. Or just the special triangles if you prefer to use that instead of the unit circle. Okay, let's sketch this. First step, sketch. That's step 1. Sketch and figure out where it is. Well, we're going in a negative direction, and I've got a fraction here, 13 over 6. Well, which is the closest multiple of 6? That's what you ask yourself, first of all. Well, the closest multiple of 6 is 12/6. Throw in the pi. 12/6 is actually 2 pi. This is close to 2 pi. Let's go negative 2 pi. So we start traveling. This gives me negative 2 pi, which is really negative 12/6 pi. But I got to go further. I got to go to 13/6. So I got to go a touch more. How much more? 1 more sixth. So inside this triangle is pi over 6. And that's all I really care about, is where it is on the unit circle, or what the reference angle is if I'm using my special triangles. So to answer the question, we go to our unit circle and we look at it and say, where are we talking about? We're talking about the 6th, the 1/6 in quadrant 4. One that has the denominator of a 6 is right here, 11 pi over 6. So negative 13 pi over 6 is coterminal with 11 pi over 6. They will end at the same spot. We're looking for sine, so I just read my y-coordinate, negative 1/2. Done deal. So I say sine of negative 13 pi over 6 is equal to negative 1/2. Finished. Determine the value of cotangent 12 pi over 5. Well, let's first of all find tan of 12 pi over 5. And then we'll flip the answer that you get. So follow the same process. 12 pi over 5, find the closest multiple of 5. And that's 10 pi over 5. 10 pi over 5, that's 2 pi. So I know I'm close to 2 pi, and I'm going in the positive direction. 2 pi around. But then that only got me to 10 pi. I need 2 more to get to 12. So I've got in here 2 pi over 5 inside as a reference angle. Well, wait a minute. Over 5, that's not a unit circle value. And that's why it did not ask me for the exact value of this one. This one I'm able to just punch into my calculator as it is. But I need to be able to visualize where it's located in standard position. So the way to solve this one, cotangent of 12 pi over 5 is equal to 1 over tan of 12 pi over 5. That's in radians. You need to change your mode on your calculator into radian mode to be able to do this question. So flip to radian mode, and now you can punch 1 over tan 12 pi over 5, enter, and you should get 0.3249, which is approximately equal to 0.32. Great question here. I would star this question. They're going to ask you one of these types of questions. It'll be a little bit different than the way they're asking here, but the concept is going to be the same. It's going to be finding arc lengths and angles from something that's going around. Like this case, this is the space station going around the Earth. It could be a pendulum swinging, some of those types. So let's look. An approximate model of a motion of International Space Station travels at that, and altitude is that, radius is that. Visualize a line segment joining the space station to the center of the Earth. So let's draw this. As soon as you got a problem solving, let's draw it. There's the Earth. There's the space station. Look how beautiful this looks. Let's put some solar panels on there. Great. So we've got there. To the nearest tenth of a radian, through which angle will the segment rotate after 40 minutes? Whew, we need to know how far it has traveled and go from there. Okay, so first thing we got to do is figure out what that actual radius of this new circle is. We've got radius of 6,400 plus 400, so the actual radius we're talking about is 6,800 kilometers. And it's traveling at kilometers per hour, and we're given minutes. We got to get those in the same units. So it's easier just to convert 40 minutes into hours. 40 minutes, well, that's 20, 40, 60. Oh, that's 2/3 of an hour. I'll use a fraction. But if you wanted, you could convert it into decimal hours. I'll just use the fraction. So now we know that distance is equal to speed times time. Distance equals speed times time. My speed was 27,600 times my time, which is 2/3 of an hour, which gives me 18,400 kilometers. That's how far it's traveled in the arc length. Now, something that's been developing all the way through in 6.2 and 6.3 is the idea that the angle, which is our radian angle, is equal to the proportion of the full circumference here. So the radian measures the proportion of how far we've gone on the arc length. So then our arc length is the angle of radians multiplied by, or I'll put theta r, or r theta. It's multiplied by the radius, and it's dependent. The arc length is only dependent on the angle that we rotate and the radius of the circle. On your formula sheet, this formula is there. A little bit disguised. It's theta over equals A over R. They give you this form. But it's really the same thing. And so our angle that we're rotating through is equal to the arc length, which is 18,400, divided by the radius of the circle, 6,800. It's a relationship of the two. And that gives us approximately 2.7058, or they said nearest tenth, so 2.7 radians. I'm going to jump over part B there. Part B actually brings in the cosine law. And I don't want to go over cosine law right now, so I will come back to that for you. All right, to finish off with, exact same questions that were brought out in 6.1. But now we're going to be talking about them in radians instead of in degrees. So our point, -4, 3. Sketch it. That's your first step. -4 and 3. There's my point P. Connect it back. So I'm rotated this way. So that gives me -4 and 3. That means my x value equals -4, and my y value equals 3. And I want to find what is our angle. So step number 1, draw it there, bring her down. We've got inside a reference angle. I need to figure out what my reference angle is first. That's step 2. So step 1 was sketching. Step 2 is find the reference angle. This is not a unit circle part because that's not on there, so I'm going to have to use my calculator to find it. In order to find my reference angle equals the inverse, and because I have x and y, I'm going to use tan. The inverse tan, that way I don't have to find what the r value is to solve this problem. Inverse tan of, and I always use the positive value when I'm looking for reference angle. Really, I'm tricking the calculator into think I'm talking about quadrant 1, when really I'm not. The positive or negative value of the fraction just tells us which quadrants we're in. That was used up in step 1. Step 2 is using the positive value, plugging into our calculator, and coming up with a reference angle of 0.6435. I got to be in radian mode here because it told me we're in radians by looking at my domain. It had pi's in there, it's radian. So inside the triangle is 0.64. Now step 3 is going to be to solve, to come up with the answer. I know that all the way to the axes there is pi. But that's too far. I got to come back wherever my reference angle is. So my answer for theta in the positive direction is pi minus 0.6435, which is equal to 2.4980. That's the positive one. Now we got to go in the negative direction. I know it's negative pi to get me there, and I got to go further. So I'm going to go further by 0.6435. Or in other words, negative pi and then add extra of negative 0.6435, which gives me an extra part of negative 3.7850. If you wanted to, you could go all the way to 2 pi and come back the value you had at the beginning. And last one, cotangent is negative 2. Let's change it into tan. So that means tan of theta equals negative 1/2. Step number 1, sketch it. I know that tan is negative, C-A-S-T, in quadrants 2 and in quadrant 4. That's step 1. Step 2, reference angle. In order to find a reference angle, we can take our inverse tan, and it's set to nearest tenth, so we know we're not looking on the unit circle here. Inverse tan of positive 1/2. The negative just told us where to draw it. This will give us theta, our reference angle. Our reference angle is going to be 0.4636. And now step 3 is solve. This is where we do our driving. So I start and go in the positive direction first to 2 pi. Oh, ran into the tree there. Stop. Quadrant 2. So I've got, in the positive direction, I've got a quadrant 2 answer and a quadrant 4 answer. In quadrant 2, I know that's pi minus the reference angle. So pi minus 0.4636. In quadrant 4, 2 pi is too far, and come back the reference angle. 2 pi is all the way around, minus 0.4636. Punched into our calculator, we got 2.6779 and 5.8195. Now we got to do the negative direction. Let's go in the negative direction. We come into the quadrant 4 answer. Maybe I'll change colors. So quadrant 4 and then the quadrant 2 answer. So in quadrant 4, we go to just the reference angle there. Negative 0.4636. And in quadrant 2, we go to negative pi, and it's still got to go a bit further. So we've got negative pi plus a negative 0.4636, which gives us negative 0.4636 in the first one, and the second one is negative 3.6052. So bring them all together as your final answer. We've got negative 3.6 to the nearest tenth, so negative 3.6, negative 0.5, we've got 2.7, and we've got 5.8. There's all the answers. Okay, 3 questions there just to bring it together for you.